Cool. Well, yeah. Hi, everyone. I'm Vivien. I'm a second-year PhD student at UCSD. And today I'm going to tell you about TickTock, which is our formally verified fork of the Talk embedded operating system. So Talk is a widely used OS. For example, Talk is used by Microsoft in the Pluton security processor. It's used in the TI-50 firmware that's running on a bunch of Chromebooks. And it's also used in many open source projects, such as OpenSK, which is an open source security key implementation from Google. Now, what's common about all the uses I just mentioned is that they're all security critical systems. So they implement things like root of trust, secure authentication, attestation, and other cryptographic services. So the question really is, how does Talk give us security guarantees that allow us to build these systems? Well, a good start is that the Talk kernel, as well as drivers, are written in Rust. And this is nice because we get type and memory safety guarantees from the language itself, which helps alleviate a lot of the classic C and C++ memory bugs that we see in the wild. Now, Talk aims to support off-the-shelf code. And this means that you can't simply just restrict processes to be written in safe Rust. But at the same time, we also can't just let processes run willy-nilly. We actually need to make sure that they're isolated from both each other and the kernel. Otherwise, one compromised process could just take over the entire system. So how does Talk actually isolate processes? Well, Talk is going to follow a similar approach to many operating systems in that it's going to use hardware. Now, Talk is designed for microcontrollers, so there's no memory management unit. And instead, Talk is going to use something called a memory protection unit, or MPU. And an MPU allows developers to define regions of memory with access permissions. And Talk uses these regions to give a process read-execute access to its code in Flash and read-write access to its stack data and heap in RAM. So that's great, and hardware helps, but unfortunately, we still need to get things right. And specifically, isolating a process with the MPU is entirely dependent on it being set up correctly. And that's something that Rust language features just don't help us with. And as it turns out, as with most things related to programming, it's really, really tricky to get this right. And unfortunately, the result for Talk has been a bunch of bugs that sort of creep in, and many of these bugs have broken process isolation. Okay, so ultimately, the reality is that correctly implementing MPU regions and sort of memory protection with an MPU is really hard. And so we need tools beyond just the Rust type system to get this right. And configuring the MPU is really just a logic problem. And so, in our opinion, verification is a great option here. So we did exactly that. We built TickTock, a fork of the Talk kernel with formal guarantees. And specifically, we use Flux, which is a refinement type system for Rust, to formally verify that upon switching to a process, it can only access its code, stack, data, and heap. Now, like many verifiers, Flux lets us write pre- and post conditions for functions in the Talk kernel that we can use to express and check process isolation. Okay, so TickTock is going to deal with two challenges explicitly. Our first challenge is to ensure that the kernel properly enforces process isolation. And specifically for that, we need to ensure that the MPU is configured correctly so that a process only has access to its own memory and not another process's memory and not kernel memory. And then our second challenge is going to be to ensure that the work done configuring the MPU isn't in vain. And specifically, we need to make sure that the assembly for context switching and interrupt handling upholds our proof of isolation. Now, in verifying Talk, we found 7 vulnerabilities, 5 of which broke process isolation. And using our experience verifying the kernel, we actually ended up redesigning some of Talk's interfaces. Okay. So I want to use an example of one of the bugs we found to explain why we built TickTock. Now, every talk process, as I mentioned before, gets a stack, data, and heap in RAM, as well as a kernel-owned grant region of memory, which is dynamic memory used by the kernel for process-specific tasks. Now, from a process isolation perspective, we want to allow the process access to its stack, data, and heap, but crucially, not the kernel-owned grant region, which you can see in red above. Okay. And the way that we're going to do that is by using MPU regions to cover the process stack, data, and heap, right? So that the process can actually access that memory, but access nothing else. Now, the MPU is a physical resource that has somewhat annoying constraints. So for example, on ARM v7m devices, region sizes have to be powers of 2. But the problem here is kind of that we have a mismatch in that the process stack, data, and heap can be arbitrarily sized. And so because of this mismatch, you might end up in a situation kind of like this, where here you can see that the enabled MPU regions give the process access to slightly more memory than it actually needs. And in this case, we're fine because the last MPU region doesn't overlap the kernel-owned grant region of memory. But I think you can surely kind of see where this is going, right? If we kind of decide that we need to grow the heap a bit, we might actually end up enabling more regions. And so what might happen is we might have a region configuration that looks something like this. And here, the last enabled MPU region covers both the heap and the kernel-owned grant region. And this is, somewhat obviously bad because now the process can actually access kernel memory. And this just totally breaks isolation. Okay. So now I want to move a little bit into talking about how we actually verify isolation. And so, as I mentioned before, Flux lets us write pre and post conditions for functions in the talk kernel that we can use to express and check process isolation. It also lets us write invariants over data structures in the kernel. And so these invariants, must hold at every instantiation and every update of instances of that data structure. And so now I just want to give you a quick glimpse of how these are used for TickTock. And of course, if you're interested in some more details, you can find those in the paper. Okay, so on the left, we have the process memory layout, which I showed you before. And on the right, we have this function allocate app memory region, which is the function that's responsible for setting up the process memory layout for any given process. Now, I don't want you to worry about how it does that. I think for now, let's just focus on what it returns. And so very concretely here, what it's returning is the start of the process's memory, so sort of the bottom of the stack, the end of the process memory, which would be the top of the heap, and it's also going to return the beginning of the kernel-owned grant region of memory and the size for the entire block of memory, which is the stack, data, and heap, as well as the grant and control for that specific process. Now, of course, these parameters sort of correspond exactly to the regions that I was showing you earlier. So this subregions enabled n variable here is a pointer to the end of the last subregion that's allowing access via the MPU. And similarly, kernel memory break is a pointer to the beginning of the kernel-owned grant region of memory. Okay. Now, as I kind of showed before, the thing that we absolutely want to avoid is this situation where the last enabled subregion is overlapping the start of the kernel-owned grant region. And so from a verification perspective, to sort of make sure that this will never happen, we really just simply need a post condition that's going to state that the kernel memory will always be after application memory. And so concretely, the spec here sort of says that if the function succeeds, meaning that it returns some and not none, then the value inside that sum variant of the option will be such that the last enabled subregion pointer is before the kernel memory pointer. Now, if we get this wrong, Flux will complain and say that it can't prove this post condition. And this is exactly what happened when we tried to verify this property. And we discussed more specifics of verifying this property in the paper, if you're interested. So now we can say something about the fact that the process memory layout is fine, it adheres to what we expect. But how do we actually ensure that the MPU, right, which is hardware, is enforcing the right memory accesses? Well, here, the same function kind of also takes a mutable reference to an MPU configuration. And this is just kind of a list of regions that's ultimately going to be written to hardware. And this function here, allocate at memory region, is going to add up to 2 regions to the MPU configuration based on the memory layout it computed to give the process access to its stack data and heap. So most importantly, each region here, so this MPU region struct, is going to have specific bits that are set in the MPU registers to sort of configure the hardware properly. And specifically here, the RBAR and RASR fields are going to hold specific bits to set in the RBAR and RASR MPU registers. Now, this region also has a logical representation of the region, that is the start and end of memory that the region is providing access to. Right? And so to kind of ensure that the hardware is set up correctly, we effectively need to ensure that the bits that we're setting in these MPU registers actually match our intention. And so that is that they match the logical description of each region, which was kind of computed by the allocate at memory function. And so to do this, we're going to refer directly to the hardware spec. So this is the ARM manual detailing what the RASR register sort of does and what the bits are. And we're effectively just going to turn this specification for each register into invariance over the MPU region struct. Okay. So on the right here, you can see we have a few predicates over registers. Now you can see that those registers are refined by 32-bit vectors because we need to sort of reason about every individual bit. And an example of what a spec might look like, you can see that RBAR start is defining the start of a region based on the RBAR register in accordance with the hardware spec, and it's using a bit mask to do that. And similarly, size is going to define the size of a region based on the RASR register. And then isSet is defining whether an MPU region is turned on based on the value in the RASR register as well. Okay. And so here you can see on the left that we've refined our MPU region struct, and most importantly, sort of added invariants that relate the logical start and logical end of the region to the RBAR and RASR registers. And so now we can kind of guarantee that if we have the right logical values, which we kind of checked in allocate at memory region, then the MPU hardware will be configured to enforce those logical values. Okay, so to kind of sum up, a lot of the verification is done through kind of like the standard pre and post condition thing, as well as invariance. But there were kind of like also many, many different Rust features that we had to build support for in Flux. And, just like kind of a taste of what was challenging, traits, were kind of a pain. There's things like const generics, reasoning about bit vectors with SMT solvers proved to be pretty challenging. And, there's many, many more details about what challenges we encountered and kind of how we solved them in the paper, if you're interested. Okay, so now I want to go back and talk about a different aspect of the paper. And to do that, I kind of want to refer back to the bug that we went over earlier in the talk. So if you remember, originally, TOC's memory allocation kind of allowed the process accessible regions to overlap the kernel-owned memory, which broke isolation. And one of the questions that I kind of want to ask here is, why does this actually happen? And I'm going to try to convince you that this is an interface problem. And I actually think that it can be summed up in the same terms that were outlined in 1991 by Worse is Better. And so, as systems researchers, there's sort of a large focus on writing simple interfaces. And Worse is Better outlines 2 interface design philosophies that have different takes on where that simplicity should be. So on one hand, we have what Worse is Better calls the Stanford approach, which favors simplicity of the interface over simplicity of the underlying implementation. And on the other hand, we have what Worse is Better calls the MIT approach or New Jersey approach, which favors simplicity of the underlying implementation over everything else. Now, like Tock's MPU interface design kind of adopts the Stanford approach. So what do I mean by that? Well, Tock's MPU interface is like super simple and it's complete. The interface works across a diverse set of hardware, and it just completely abstracts away the hardware complexity constraints from the interface user, which is like really nice. It's great. But there's sort of a consequence, which is that the interface ends up being monolithic in the sense that it kind of tries to do too much at once. And specifically, what Tock is doing here is it's entangling memory allocation and memory protection. Now, intuitively, this kind of makes sense because memory allocation and memory protection are interconnected, but this also means that the implementation is bound to be super complex. And crucially, like this complexity is really where we found most bugs. Now, interestingly, it turns out that actually it was really, really difficult to verify this complex implementation. And so, some functions took like over 5+ minutes of SMT solvers grinding away to verify. And additionally, we found that, even though the interface was really simple, the specs we were writing weren't. And, this is because the verification tool sort of like is going to blast away all the interfaces that you have. It just doesn't really care. Specifically, like we're forced to lift some of the hardware constraints into the specification and across that interface because hardware is ultimately what's giving us sort of the global invariant of process isolation. Okay, so how can we make things easier? Well, I want to bring up something that we discovered in our work, and that's that pragmatic verification of existing code requires breaking monolithic interfaces that seem to belong together into simpler modular components. So what do I mean by that? Well, on one hand, we have the current Tock MPU interface, which is going to mix memory allocation and memory protection. And again, this is intuitive because the two are closely related. But entangling these two makes the implementation like far too complex, and it doesn't properly capture the isolation enforcement mechanism, which is MPU regions. And so instead, we think that we should split memory allocation and memory protection into two separate interfaces. So first, we have a new MPU interface, which lifts MPU regions to the language level. And this is way easier to get right because there's only one concern to deal with, not two. And then we have a dedicated memory allocator. And the nice thing here is that the allocator actually has the same interface as the original Tock MPU interface, but its implementation is now going to use our new MPU interface in a layered manner. Note that this is also now part of the kernel. So on one hand, the kernel is going to have to do a bit more work and get a little bit messier because it needs to deal with some of the hardware specific details that the MPU abstraction exposes. But overall, we think this has a lot of benefits. So separating concerns ultimately makes verification easier because we can reason about protection and allocation separately. And this also makes verification faster. So I told you earlier that individual Tock functions took over 5 minutes to verify. Well, Flux checks all of TickTock in around 30 seconds. And not only that, but it actually turns out that this new design unlocks some performance gains on some critical code paths. And this is because there's cost to Tock's simple interface that's kind of sprinkled throughout kernel code, and we're able to remove that. Okay, so I want to finish up by sort of talking about how we prove isolation in the presence of context switching and interrupt handling. So in practice, verifying Tock interrupt handlers uncovered some more bugs. So for example, we uncovered a case where the CPU's execution mode wasn't properly changed to unprivileged execution when context switching to a process. And that ultimately meant that the MPU that was so carefully set up by the kernel was actually turned off. So the question is, how do you make sure that this doesn't happen? Well, once again, our answer is to verify, and we do so by developing FluxArm, which is a Rust executable formal semantics for a portion of the ARM v7m ISA. So specifically what FluxArm does is it lifts assembly instructions and hardware semantics from the ARM ISA to Rust, and then we use Flux to specify semantics for each instruction via pre and post conditions. And then finally, using these semantics, we're going to lift talk assembly programs to FluxArm and verify their behavior. And using this, we can also model aspects of talk's control flow from the kernel to the process and back, and then check that all the kernel registers at the point of the context switch are properly saved and restored. Okay, so a correct MPU configuration, along with correct context switching and interrupt handling, gives us strong process isolation. Now, if there's one thing you should take away from this talk, it's that verification unveils complex implementations that hide behind simple interfaces. So specifically for us, it was our experience verifying the original talk code that helped us break an originally intuitive abstraction into multiple modular components. This had a variety of benefits. It simplified the implementation of both memory protection and memory allocation, which in turn led to a simpler spec, faster verification times, and even faster runtime performance. Thank you.
Thank you so much for that presentation. While I wait for some questions to pop in the chat, I had a question of, now that you've kind of gone through this experience of finding a bug in talk, are there like other commonly used programs or software that you suspect also has this issue of the interfaces are a little too simple and that you might suspect have like similar sorts of bugs?
I mean, that's a great question. I'm not 100% sure. I mean, I would assume so, but I haven't like actually taken a look. I mean, one thing that I think would be potentially interesting, and I think is kind of happening, is taking these verification tools and kind of pointing them at more and more systems. So like AWS has the Rust Standard Library Challenge, which I think like a ton of verification tools have sort of joined and are working on. And then, I think there's a lot of systems like maybe like Firecracker, potentially even pointing these things at browsers now that Rust is kind of like entering, things like Firefox. And it'd just be interesting to see if like this sort of pops up. I think like one thing that's interesting is like, as a programmer, you don't necessarily like find these things. You only like it seemed like from our experience at least that you start to find these when you need to do this sort of verification work, because you start to care like really deeply about what's behind the interface. And then you go, oh wait, like that's weird, right? And then it takes like a long time, at least it did for us, but eventually you sort of start to figure out maybe what makes more sense.
Thank you so much.
Yeah.
Doesn't look like we have any other questions. Thank you for your presentation.
Yeah, thank you.